Dijkstra. Do you know what it is? Well, you should do if you watched episode 2. We got into it. It was good. So what have we got going on for episode 3?
So in episode 3, we're doing part 1 of the how-to. How does Fabric Connect work? And in there, we're going to deal with topics like the control plane, the forwarding plane. We're dealing with the principal protocol, which is ISIS. So it's getting a little bit meaty, but it's going to be a really interesting episode. Really good.
Are you ready?
As ready as can be. Let's hit that studio.
Let's do it.
In 1998, the IEEE gave us 802.1q. And for the first time, we were able to have a virtualization networking technology that sits on top of a network, most commonly known nowadays as VLAN. In 2005, however, the IEEE came up with something called Q-in-Q, or provider bridging, and that was on the 802.1 AD standard. What 802.1 AD allowed you to have 4,096 VLANs inside every virtual VLAN. Now notice that it was a VLAN inside another VLAN. In 2008, they gave us 802.1 AH, provider backbone bridging. This was known as MAC in MAC. There they gave us just over 16 million service IDs, no longer embedded a VLAN embedded inside another VLAN. Those two became quite popular, and eventually in 2012 they merged the 802.1 AH and the 802.1 AD into one standard, which became the 802.AQ, which we referred to previously. There they're using the ISIS protocol, which is one of the oldest protocols around. Unlike some other protocols, for example, OSPF, it wasn't written for IPv4 or for IPv6. It was abstracted from that. It could work on anything. And when IPv6 was established as a standard, OSPF needed to have a different version that was written specifically for IPv6. Then in 2007, the IEEE also came out with a connectivity fault management standard that was used to troubleshoot these virtualized networks. That was called the 802.1 AG. All of those standards eventually led to Fabric Connect. ISIS is what is commonly known as a link state protocol. Now, what is it and how does that work? Well, a link state protocol forms adjacencies to its neighbors. So how could I explain that? Imagine if I moved into an area and I have 2 neighbors, one on each side. And when I move in, I go and speak to them and I introduce myself to them and I say, hey, I'm Isaac, I got a family, I drive this car, I've got 6 kids, this is who I am, and I like to drink tea. And then I go to the next door neighbor on the other side and I tell them everything about me that I told the first one. Well, the first neighbor would then probably tell me all about them, and the second neighbor would tell me all about them. And so what I could then have is I could have a really good picture of my neighbors, of who they are, what car they are, where they parked. I could have all of that information. In ISIS, these adjacencies, that's what happens when you turn on a switch and it's got ISIS. It talks to its neighbors and it uses a link state database to get some information, some specific information. Of course, not garages and all of that. I'm just using that as an analogy, but it uses type length values and they advertise things like the system ID. So it sends out its system ID. I am this switch. This is my switch number or my MAC address of the switch, my ID, my unique identifier. It sends that information out. So by sharing this information with its neighbors, you can see what happens every time a neighbor comes into the area. Every time a new switch comes into the area, it talks to its neighbors and it exchanges this information. So if it does this automatically, what it's really doing in the background, it's building a topology map of the area in which it is operating. And each switch then knows exactly, synchronizes all of that information. And that's why when you add a switch into the network, it can instantly or within 200 milliseconds advertise all of that information, learn, and update that topology map. And from that topology map, then we use Dijkstra to calculate the shortest path to all of my neighbors. Now, of course, like we saw in those examples, if my neighbor is 10 away, 10 units away, it knows there's my neighbor. That's who I'm connected to, that's the shortest path. But if I have a neighbor that is 3 streets down or 2 streets down, well, Dijkstra has done all of those calculations. And by doing all of that, it knows when I need to speak to that neighbor, to that switch over there, when I need to get some packets across, it will know exactly which is the best path to take me to that place. So shortest paths, as we saw, are based on link metrics, costs, whatever you want to use as a terminology for that. We have unicast, so within the ISIS protocol, we have unicast paths that are calculated to every single node. They also calculate service-specific paths or routes for multicast delivery trees. You have symmetrical data path between any 2 nodes. So if I talk to my neighbor along this path, my neighbor will talk to me along the same path. So that's really clever mechanism. It doesn't talk one way and then respond another way. It also creates BMAC forwarding entries for BVIDs. And here's a really interesting thing about the fabric control plane. There's no IP configuration required inside the fabric. Essentially, the network becomes a virtual switched fabric with absolutely no blocked paths. Because why? We don't have any loops. We don't have spanning tree protocols. It doesn't exist within Fabric Connect, within this control plane. Now, shortest path bridging enables a service-orientated networking infrastructure. That is the forwarding plane, which is based on 802.1AH or Mac in Mac, and the control plane, which is based on ISIS, the protocol ISIS. In contrast to the standard and traditional way to build networks, where the protocols are stacked one on top of the other, and there's an interdependency on the lower stack. So if one of the lower ones fails, everything sort of crashes. The SPB layer can run over almost any infrastructure, even infrastructure which themselves are layered. For example, MPLS, it can run over fiber, copper, you name it. The SPB can run over it. So we can see that with SPB, we have a really good standardized technology on which we build Fabric Connect. The forwarding plane is going to be responsible for shifting data across this Fabric Connect network. We have to establish virtual services networks between the different endpoints of this network. And that could be different things for different types of organizations. If you're a business, well, or if you're a campus, a university in a campus, well, you might want to create virtual services networks between 2 groups of people in different buildings. For example, HR networks. You might have HR offices in 5 or 6 buildings throughout your university, and you'd like those people, those offices to be connected together. So you could create a virtual services network that hooks up to each one of those devices, to each one of those BEBs, backbone edge bridges in those different buildings. And by doing all of that, you hook them all up and connect them all up together. Now, those VSNs, those virtual service networks, would each have a unique ID. And those unique IDs we call an ISID, ISID. It's a unique identifier for that virtual service. And the other thing about it is that it separates the traffic from that service being accessed by any other VSN. Only those BEBs connected to that ISID or that have that ISID as an identification can communicate with each other. No one is allowed, no other virtual service network is allowed in there. Ultimately, what that gives you is hyper segmentation of a network. And anybody who works with security will tell you that that's the holy grail. All the configuration that you're going to do on a Fabric Connect network is going to be done on your backbone edge bridges, not on the core. You never touch the core. So you're just doing this work on the outside. You create your VSNs, and once those VSNs are set up and ready to go, you can instantly start communicating. So you now have a user that wants to communicate, that wants to send a data frame, a packet across the network. I mean, we don't really want to do that. We want to print or send emails, but it all goes down in packets or frames. So on screen, you can see an Ethernet packet. And in the packet, you can see it's got a payload and it's got a source address, SA, source address, and a DA, of course, a destination address. You need that, just like you have in a letter. When you send a letter to someone, on the front you put the destination address, and on the back you write the source address. Ethernet frames are exactly the same. Now, if you are using VLANs, and possibly you are because we spoke about customer VLANs, at that point you might use 802.1q to put a VLAN ID into that particular frame. And at that point, you're saying, I belong to this virtual LAN 1076, for example. It could be anything. So that is the customer packet as it leaves the computer and as it enters the BEB. And it enters the BEB using the UNI interface, the user to network interface. So it enters the BEB on that switch, and now the switch does the job of the forwarding plane, because now what it does is it grabs that packet and it does the work required for this encapsulation, this Mac in Mac encapsulation. And you can see on the other side of that switch, on the network to network interface, what comes out of that interface is the same packet that went in, but now we've encapsulated that and we've added extra information into that. But now as that frame comes out of the NNI port on that switch, it now encapsulates extra data into that frame. It's still got the payload, of course. It's still got the original source address. It's still got the original destination address. It's also got the customer VLAN ID encapsulated in that frame. It's got all of that information. But look at the new information that's in that frame. It's got service identifiers. It's got the ISID identifier, that unique connection, that unique virtual services network that's been allocated to different offices or to different groups of people. It's got that information inside of it. It's also got a BVID, a backbone VLAN. Remember we said that BCBs, they communicate using the backbone VLAN. There are two of those, and they load balance between them. They send data across both of those at the same time. So it's got that information. Which highway is it traveling? Is it traveling on Highway 1 or Highway 2? Well, this one is traveling on Highway 1, and all those frames coming from that client will be put onto Highway 1, and they will make the route to its destination. What else does it have in there? It's got the backbone destination address. By that I mean it's got the destination address of the BEB on the other side that's going to be receiving this. And it's got the backbone source address as well. So it's now coming from switch A and it's going to switch B. It's got all of that information that then gets encapsulated. Think of a gift that you get at Christmas. Think of taking that gift and rewrapping it and adding extra information onto that. If I send something to South Africa, for example, then DHL is going to take it, and especially if it's something big, they want me to put extra information in there. Even though I put the destination address, they encapsulate it. They put it inside one of their bags and they seal it, and this is what it's doing. It's taking that original frame, encapsulating it, sending it out of the BEB with the origin address of the BEB, letting it go through the Fabric Connect network with the destination address, and off it goes only on that ISID, only travels along that ISID. And that's how it gets to the other side. That is the forwarding plane on Fabric Connect. Network engineers absolutely love the command line. They love typing commands and they just go on for lines and lines and lines. It shows off their skills. I don't blame them. It doesn't mean that network engineers who work on Fabric don't love that too. They do, except that they have a whole lot less work to do anything significant on the network. So on the screen, you see two customer VLANs, VLAN 10, and to connect these two VLANs together, all you really need to do is to map the customer VLAN to the service identifier of the virtual services network. So in this case, that's VLAN 10 needs to be mapped to ISID 210. Why 210? Well, there's no meaning to that. It could be any number. The system could even generate a number for you if you prefer. It's automatic. As soon as the mapping to the ISIDs are completed or defined on the BEBs, the backbone edge bridges, the switches on the end, then ISIS automatically calculates the shortest path to the destination, the shortest path to where it needs to go. And the traffic immediately starts being forwarded along those routes. This is as simple as it is. So when I said that a VSN is really simple to set up, I mean, I wasn't kidding. It really is simple. You literally need one single command. Watch this on screen. First thing you do, you're going to create the VLAN. Now that's different, right? So there are two commands to go ahead and create a VLAN. It's VLAN create 10 type port. The second line would be VLAN members add 10 to the fourth chassis first port. And then we go to the one single line that sets up the VSN between these two VLANs. So VLAN space I-SID space 10, which is the number of the VLAN on this side, and you give it a VSN number, identity, like 210. Does 210 in itself mean anything? No, it's just an arbitrary number we're using for this particular example on screen. Do the same thing on the second side, same command, and voila. Does it actually get easier than that? Does traditional get easier than that? Let's talk a little bit about services running over Fabric Connect. When you have a VSN, a virtual service network, there are certain types of services that you can run on that virtual network. One of these is layer 2 VSNs. As most people know, is a flat structure, very fast, interconnecting LANs, interconnecting different offices without any specific routing. So you really are extending a VLAN across the entire fabric. If you're in a small office, when I say small, we could talk about 2 floors or 3 floors even, that would be termed small. You can see that extending these VSNs doesn't sound like such a big thing when you're connecting different offices. But if you're running a university campus, if you're running a hospital that has got multiple buildings, if you are working in government offices that has exactly the same scenario, different offices, different buildings in a same city or so, you can quickly see how extending a VLAN across an area becomes really useful. The other thing that you can run on a VSN on one of these services is, of course, multicast. Now, multicast most often is used for video. You would have a VSN, for example, and you could create that VSN to hold all your CCTV security footage. That could all be done on your VSN. And then you can share that content with others that need to get access to that content. Now, multicast is traditionally not that easy to set up. If you're in the networking game, you need PIM, and I've never ever spoken to an engineer who smiles when I say PIM. It's almost under their breath, they swear at me, because PIM is ridiculously difficult to understand and set up. But within Fabric, once you create your VSN, it's really easy. Your multicast follows the same route as your unicast. It is really very easy to set up multicast. And a lot of our customers, when they see that type of functionality, it's almost the thing that swings it to buy Fabric Connect. Just how ridiculously easy it is to create multicast. In multicast, you're going to have one ISID for each source and each group. As simple as that. I think I mentioned previously, networking engineers and IT people in general are not that great at naming things. And I think this is a pretty good example of that. So there's this feature within Fabric Connect called IP shortcuts. So what are IP shortcuts? Well, if you look at this diagram coming up on screen, you'll see that I've got two different subnets, okay? Two different customer VLANs, a VLAN 70 and a VLAN 80. I want to connect those together using a GRT, a global routing table. I want to connect them with that. So a node will utilize ISIS for IP route distribution of the global routing table. So if you need that functionality, ISIS is able to do that for you. You don't need an ISID. It's not necessary to have that, but it applies only to global routing tables. With the IP shortcuts, you also have multicast. Multicast is supported within IP shortcuts. The BEB is going to create a multicast ISID, even though it's not necessary for unicast. For multicast, it's going to create a multicast ISID, and again for each S and for each G, for each source and for each multicast group that it needs to send the information out to. It's not an easy concept to understand, but if you want to know a little bit more about IP shortcuts, there's two things that you can do. Either send us an email and in the subject line, just put IP shortcuts to learn at extremenetworks.com, or alternatively, scan this QR code and it will take you to our webpage, our Extreme Networks webpage, where we reference this information and this technology in more detail. And if you really want to jump in and get to know what IP shortcuts are about, this expands it a little bit more. Fabric Connect is a technology that thrives on agility, on scalability, and flexibility. So in today's episode, we added a whole lot more acronyms to our current account. Did you get them all? MPLS, ISID, VID, CVID, BVID, BDA, BSA, GRT, and L2VSN. Whoa. See you in episode 4.